for Twitch here, I expect things to be broken because I updated the latest Mac OS. Let's see if OBS got it right this time. All right, we have a picture. That looks the same for both of us. So we're gonna have to rock like this. Today is the 17th of September. We are just kind of we just launched a module on return-oriented programming and wrapped up reverse engineering here at ASU for CSE466. I did not prepare the memes this time. A TA did for me. So let's see what the TA said. They didn't even put memes on the slides. I just copied the slides. Okay, so classic, right? I'm going to do everything early, and then you end up not doing that, especially since the checkpoint got pushed back. Sad but unfortunate truth. And then the flip side of that. Hey, the checkpoint got pushed back. I had time to make up some stuff. Maybe I was busy, and it turns out I actually got some stuff done. So maybe it's win-lose there. It was kind of interesting to see how people felt about my Disassembler rant because I mentioned it several times. I have been signed out. Oh no. Nothing good happens there. Okay. We're derailing. We're derailing before I even tried. Oh, instant win. Okay. So I talked quite a bit about writing a disassembler, how this could be useful, particularly for 21-22. You didn't get 21 because I made a typo, so bank in your favor. But having the ability to generate YAN code, so not the disassembler, but the reverse operation, which is very similar code, will pay dividends in the future. So we at least have that. In truth, like when I solved these challenges, because I did end up having to solve them way back in the day, I didn't write a disassembler, right? But it is what most people tend to do. I also didn't use IDA, as you can imagine. If you thought about the challenge, it had a good head as far as like where is the critical part that matters. You could solve it with just some GDB script and printing out critical values for several of the 1920 levels. And so some people figured that out. So right on. You'll still want an assembler for the record in later parts of the course. But you didn't need it right now. I have IDA and then the cooler IDA. Do you guys actually like GDB? Yeah? Yeah? I'm actually converting some people? Everyone else thinks I'm crazy. I'm glad some people are starting to see the light there, that there's a lot of power to dynamic analysis if you are able to articulate your question. Me at level 1. I can do this. GDB, don't need you. GDB, use IDA. GDB. All right. For the record, if any of these are your memes and I didn't like it, message me and I'll give you the old update. After completing reverse engineering, technical skill, YAN 85. Okay. So hopefully people do have a good idea of how YAN 85 works to some degree. It is pretty well known. This is your meme? All right. Well, the TA thought it was a great meme.
I was proud of it.
You're proud of it?
Yeah.
It feels good when your meme makes it on the show, doesn't it? Yeah. That was one of my big motivators back when I took the course, was just to get goofy things on screen and make the instructor comment on it. And Dad, why is my sister named Rose? Because your mother loves roses. Thanks, Dad. No problem, YAN 85. I can't believe anyone actually loves YAN 85. Yeah, maybe it's kind of a Stockholm syndrome thing. You just spend too much time with it. But yeah, at least we're having fun with it. Okay, 22.1. You realize you're trying to solve the challenge by figuring out what the level decided to map register syscalls, opcodes, one massive matching puzzle you've been duped into solving to make a valid Yani 85 shellcode. That's very true. So one of the things that was asked like a module ago was like, these are the last challenges of a module. Is there like some big bait and switch, some secret technology that you have to know, some man page, some secret knowledge is hiding on a slide somewhere that's necessary? If the challenges are designed well, the last challenge doesn't require like some super secret knowledge. It's clever application of things you already know and thinking about the concepts at play and how you can utilize that knowledge differently. And as some people noted and mentioned on the Discord, one of the key pieces of information to solving this was figuring out what was a clean exit code. It was one of the critical pieces on kind of deducing what's going on inside of this bad boy. Rob, so I did notice this. People are starting earlier, which is a good sign. I'm actually quite pleased with what I've seen so far as far as people taking the start early to heart. And so that's awesome to see. Okay, I haven't thrown up a schedule in a while. We are here. So we are on return-oriented programming, which is slated for 2 weeks. In my personal opinion, Twitch, blank. GDB is clutch. You like IDA as a backup? No, IDA has its place. Most people prefer IDA. But we're on return-oriented programming, which is slated for 2 weeks. In my personal opinion, it very easily could have been a 1 week module. We're going to run it for 2. I don't think you'll need it. So it'll probably be a pretty chill 2 weeks. That doesn't mean slack. It means work on it and enjoy the benefits next week. Grades. How did we do? I mentioned I was pretty happy with the solve rate. If we look at this, I didn't put on the last module, but a lot of people started in the first 3-4 days here, which is awesome. And as one would predict, the people that started at the very last weekend, they didn't make it very high up. But as a class as a whole, it looks like we're cruising at a decent rate. One of the things I find kind of amusing is this kind of line where everyone just kind of flatlined. Anyone want to guess roughly where that ends up? Yeah. The comment for Twitch was 17 or 19. I don't know which it is because I didn't bother to do the actual math, but it's 3/4 of the way through. My guess would have been 19. 17 you can get there. 19 does require quite a bit of effort, but that effort pays dividends in the later challenges. Did you disagree? No, you're welcome to. You're welcome to tell me I'm wrong. Yeah. Okay. But it definitely was I think we just kind of drew the line and stopped there. We said it wasn't worth our time, which is totally fair. Aim for the grade that you want. This is not the grade distribution, for the record. This is a solve distribution. So I'm not including that bias of the checkpoint here. So just this is what percentage of challenges did people solve. And as we see, a very large amount of people solved everything. And I think it's reasonably safe to say majority of the class solved 60% or more. Remember that with that checkpoint, if I can assume that these people got the checkpoint, that's a 15, 16% swing on top of that. So if somebody is in that 60 to 70% range, with the checkpoint, that's really 80, 85. So realize that the actual grades are actually pushed even further to the right. And I did, just for transparency's sake, if somebody didn't solve anything, they didn't go on this graph. So this right here are people that solved at least one. Grades overall. So this is course grade distribution. So this is including the checkpoint bias. We see a similar distribution to what we have there for solve rate. However, we're bifurcated a bit more. In my kind of interpretation of this, the far left-hand side is mostly just, hey, the first module crushed me. But more people are moving to the right-hand side. And so I take it as we're probably fine. Like, I'm not horribly moved one way or another at this distribution. Aside from the people that are right here, at the 0.4 to 0.5. Like, that's just a rough spot because of the checkpoint in general. But that's course grade, so who knows? Logistics, average course grade right now across the course, excluding extra credit, 74%. Remember, if you play ball, you get an extra 15%, and then I gave you a 1, so that gets you, what's that, a 90? Like, I'm perfectly fine, cruising right around where I'd expect. Extra credit, I think last week I said I was working on getting the memes extra credit and thanks extra credit onto the grades page in real time. I haven't finished that just because I juggle a bunch of things. I still lie to myself and say it's going to happen at the end of this week. I do have a branch so you can at least look at it and tell me I write horrible code if you want to do that. I had my office hours. Last week I announced the room that it was in. That's going to be in PIE 222. We're doing that Friday from noon to 2. Last week I said it may or may not be streamed, kind of depended on what happened when the students showed up. Like, what were we stuck on? What did we want to talk about? Based upon how the first one went, the conversation was very specific to challenges. And if we're going to have a specific discussion on challenges, I can't stream that. Now, that doesn't mean that everyone got a whole bunch of free code. Like, we went back and forth and we said, hey, what are we thinking? What are we doing? And built it up. And so it will not be streamed, but I think it will be exceptionally helpful for anyone who can attend and you're looking for that type of interaction, right? You get that hopefully in recitation with the TAs where they can sit down, look at what you're doing, get you squared away, or at least get you pointed in the right direction. For the office hours, I'm trying not to go exclusively one-to-one, but just like, hey, where's your pain points? And then let's start moving and get something in that direction. If for whatever reason you have a scheduling conflict and you're like, hey, I still want to try and get some one-on-one FaceTime to figure something out, let me know. This semester I am on campus a few days a week, so hopefully we have something where we can schedule it if it's needed. One of the unfortunate things that kind of came up over the course of this module, and I'm sure this won't be the first one, was some kind of strange behaviors I noticed as I was working with people. Now, the dojo is a very complicated and fancy piece of software. If you ever want to check it out, one of those, a side effect of being complicated and fancy and trying to do all of this to give you all dedicated Linux environments as we work on it, is sometimes things don't behave as one would expect. And unless students surface, hey, this isn't working right, and I say, oh, well, just do this. If you don't tell me, no, like, I'm doing that, then I just assume that you solved your issue. And so if you feel like hey, there was an issue, and I said, hey, you're doing it wrong, I empathize now because I have seen that. Working with people during recitations, I try and show up to a recitation once a week or so. I recognize that some of this pain could have resulted in you spending undue time fighting GDB or GDB scripting. As just a blanket cure-all, and this goes back to the grade, we're going to deal with it and then we're going to move on. There was a problem. I recognize it could have ate some of your time, or you could have made progress in other challenges. So everyone in the class will just get a 0.5% extra credit. Is that fair deal? Everyone just gets it for free. It's not on there yet. I'll try and add it tonight, assuming I don't immediately pass out when I get home. The key takeaway here is add these 2 lines that I have on this slide to your GDB init. Because of the way the Dojo works, there's some complicated things with paths and symbols and where some stuff is located that is not the same as like a Linux VM if you were to install it. Adding these 2 lines to your GDB init fixes those things. What problems do they deal with? I can kind of show you. So one of the things that I showed on stream was using, hopefully I still have it. Yes, was doing something like this with a GDB script, where you set some arguments and you call printf and then it displays it. I was working with someone in recitation, and they had the same thing as me. We were running them side by side. Theirs didn't print anything. Mine did. This first one here is the solve for that. It turns out GDB needs to know where some debug information is, and on the Dojo by default, it did not have it. So that's why that's important. The second thing, which is a bit easier for me to demo without wasting too much time, has to do with setting breakpoints. And I know there was somebody that commented about this on the Discord because I remember the comment. Let's find, what am I in? Shellcode injection? Okay, so bincat has to call open. Not you, this one. Let's see if we get the behavior I'm looking for here. A reasonable thing you might want to do is set a breakpoint at open or break it, say read, and then run it. Well, that happened to work. That's unfortunate. Because the behavior that I was expecting, it was specific to memcompare in the Yani 85 challenges. Something that you may have wanted to do, and it was totally reasonable, is set a breakpoint at memcompare. And GDB would say, hey, you set a breakpoint at memcompare, you would then run the challenge, and it wouldn't break there. The reason for that is because GDB was looking at the wrong libc, the wrong library for where should these shared libraries be located. And because of that, it wasn't thinking correctly about where things are, and so it was setting the breakpoint at wrong locations, and it wasn't working. Now, these things will happen, and I try and be a fair person, which is why I'm given the 0.5 extra credit. But the counterpoint here is that isn't an absolute deal breaker. If that happened to you, hopefully you worked around it. What did you do? Or what could you do? I can't just go break memcompare.
You can find address of tags from IDA.
Okay, I could use IDA and find where the called memcompare is and break at the address in the binary. Whether that's from the binary symbol plus an offset, which would not be impacted by this, or by specifying the hard-coded address, or doing like the base plus something, right? Any of those totally could have worked. It would have been a way to get where you needed to. So I don't consider it like this insane deal breaker because there's more than one way to skin a cat. And part of what you're trying to do in this course, or hopefully learning in this course, is how to kind of adapt and work through problems that you aren't familiar with. Things will break. Things will break not only because of us, but things just break in the real world. And so I don't consider it this like absolute OMG, we need another week kind of scenario. But I recognize that, hey, maybe you would have solved another problem or two. And so I consider this a fair compromise there. Now, someone is not going to watch this stream. And they're going to mention it like 2 weeks from now. And I'm not going to remember what video it was. Other logistics. So I think Rob's pretty easy. I said this with Rev, and then other minds convinced me to not do this. Hey, at least it's 0.5% extra credit. Exactly. GDB is cursed. There's a lot of things that are probably cursed this year. We're gonna learn together, right? Part of the fun. I really think I am gonna add stuff this time. We'll see what happens. Same rules apply. If I add it, it's not going to be in the first week. If I add it, it's not going to push the checkpoint. I think it'll be fair. Does anyone have anything that you want to hit me with? Yes.
Just on the Rob Dojo, is it possible to add like the countdown? So we can really see it?
Yes. So that's I didn't put a due date on it. That's why you don't see it. There is one. That was part of why I had to throw a schedule on here. I appreciate the reminder. I'll get to that tonight. So sometime after class, I'll add it. It'll be midnight on the 30th. Checkpoint is going to be the 7 days or 10 days, whatever our standard was that was set on the syllabus there. I think it's 10 days, which is we ignore the weekend and then it's 7. So what does that land on? 23rd? What's that? Next Monday. Yeah. How many people have taken a look at Rob? That's quite a few. That's good. So was there anything about reverse engineering anyone wanted to? Oh my gosh, we're stuck. We're good there, because we're going to shift gears back towards what we kind of did in the first module. ROP is kind of a natural continuation of what we already did in the first module. So let's take a look at that. Okay. Maybe. I have to remember to split this way so I don't cut myself off. All right, so I have this binary here. It's pretty boring. We got a main function. I haven't tested it, so we'll see what happens. We're going to read into some buffer, and then it's going to return. This should look somewhat familiar when we think about the first module. What do we recognize about this? There's a buffer overflow. So I can overflow by reading into buff more than this 256 bytes. What things do I want to know about this buffer overflow?
The address it starts at.
I'm sorry?
The address it starts at.
The address it starts at. Okay. What is something I may want to try and exploit or take advantage of? The return address. What's something that might stop me from doing that?
Stack. No.
The stack canary. The stack canary. So one of the comments was executable stack. Executable stack matters if we're going to execute shellcode on the stack. Shellcode used to be how exploits were done forever and a day, but it's been, I don't know, a decade, maybe 2, since shellcode was something that was really used in the majority of like real world exploits. Because we came up with the NX bit, the stack can be non-executable, that pretty much shuts down shellcode. Okay? There are some edge cases, which I think Jan mentioned, like a JIT. Everyone know what a JIT is? A just-in-time compiler. So that is the one weird scenario or one hyper-specific scenario where you may have a region of memory that's mapped writable and executable at the same time. Although a well-written JIT should have one or the other, right? It should kind of remap and change the permissions. But if it's high performance, like performance is a big factor, you may end up with writable executable. The thing that matters for what we're trying to do here is the canary. And we can see if we have a canary with checksec. Looks like we do not, which is a good thing, because if it did, we wouldn't be able to get very far. So I want to overwrite this return address. How do I do it? Hopefully you did this in the first week. All right, you did something. Okay, how do I need a bunch of A's plus an address. So what do you want? Echo A. How do I know how many A's? Like, you're going to be driving the train here, all right, until we get to the new stuff.
One thing was you showed us the source code, so we know that there's 256 bytes that the buffer is going to take, and there's no canary, so you can pass it 256 A's plus the return address of the win function, which you can get through GDB.
Okay.
And one more thing, probably it also has an RDB, so in between the buffer and the return address, put like 8 bytes per pure.
Okay, so I heard a couple things. I'm going to repeat for Twitch. They said, Robert, you showed us the source code, you fool. All right. We saw the buffer's 256 bytes in size. And therefore, if I send 256 A's into this plus something, I'll overwrite the return address. Somebody else commented and chimed in, hey, wait a minute here. The stack frequently has the saved RBP on there. So it should be 256 bytes plus 8, and then I get to the saved return address. All right. It could be correct. I ran out of time. I didn't actually get to test this bad boy, so we'll find out. So if I print, get my quotes right here. I know I'm cutting you off. Bring it down here. Print A times 256 plus A times 8 plus, let's put a B there. B times 8 plus, how many C's do we want? 8. That should be the return address. And we ram that into, I'm going to mess up these quotes. A dot out. All right, we get a segmentation fault. All right. It's lame showing you the source code. How else could I have came to this number? I don't actually know that's what happened. But yes.
You could go into GDB and see where the return address is being called by the return function.
Okay, so I could GDB the binary. We could run it. And then what? So right now it's waiting for input. Do I need to dump in a whole bunch of A's?
Control C.
I could Control C. Now where am I? GDB is not very happy there. I know I'm in read. GDB is not very happy, probably because of the GDB init magic I just said you must have. Yeah, you win some, you lose some. So I'm inside read, and I could look at RDI. Is that what I want? If I'm not sure, I could go to the man page, and so we could man read. I want the second argument, because I'm interested in this buffer location, right? Where is it? RSI for the win. So, there's my RSI. Now what do I want? I'm going to Finney. This will run all the way through read. It's blocked on some input. Doesn't matter what I get. What I really care about is getting back up into main. From here, we can info frame, and this tells us where that saved RIP is. So now, this was my buffer. This was my saved RIP. Hopefully, we get the same number when we subtract them. Hex 108, that's printed as a decimal. 264, and then what was 256 plus 8 as a decimal? 264. So we came to the same number. And there's a few other ways you could have done this. We could have used a cyclic value. It doesn't matter. I just want to make sure that you recall them because we're playing the same game. Return-oriented programming is a specific type of memory corruption on the stack. And you've kind of already done it. You just haven't done it as a style of programming. So we have in my source code that I spoil you with, I have this win function. So hopefully I didn't make it SUID. Let's do that so that this is actually solvable. How could I get the address of win? All right, because if I can overwrite this return address, win's probably a good place to go. Object, we're old school. All right. Object dump, disassemble, a.out, except that's going to be completely unreadable. So mintel. Let's see if we can be a little bit clever there. I can grep the output of object dump for win, and I get this address. What is a important thing to know about this binary and this address? Okay. So the comment from the class here was PIE, or PIE. Does everyone understand the difference between PIE and ASLR? I'm getting some faces. Now is the time for us to cross that bridge. So they work very similar. They have to do with whether or not stuff is randomized. Okay. PIE is a compilation option. This is something that you decide when you run GCC. So this is the command that I ran to make this executable. And you'll see that as a flag to GCC, I put no PIE. This is something that's decided when the source code is turned into an executable. PIE means that when we look at the instructions, let's see. Trying to find a good example. You'll get addresses that only resolve to a fixed point. Okay? So it has to do with the actual assembly instructions that are emitted by the compiler. If something is PIE, what you end up with is a whole lot of addresses that look like this. They're RIP relative. What using a RIP relative memory address means is that it doesn't matter where that assembly code is located within memory, that mapping will always be correct because it's a fixed distance from the binary. So this doesn't have PIE. And so the ELF is always mapped to this 40,000 address. If I were to compile it with PIE, this address would change every time. And that's why when we're referencing a memory location, this right here, this read executable, this region of memory is where the text section is. This is where those assembly instructions are located. And so if I need to reference something in memory, and we're constantly shifting this thing around, if I'm referencing it from where I already am, it's a constant distance. Now, one of the things that people asked on the Discord right before class was, if I get a leak, what does it mean? How do I make sense of this? Now, they were asking about the stack, but I'm going to use this region of memory here for demonstration purposes. If I get a leak of something in the text section, right? So in this red section here, I get some pointer between 41,000 and 42,000. What does that tell me? It tells me the literal address that it prints out, obviously. But is there anything else that I can infer about memory based on that number? Well, VM map or proc info maps or any of this type of memory layout is showing us these regions of memory. But these regions of memory are displayed to us based upon the permissions. An important thing that people often overlook is this is 4,000 to 41,000. What's this next one? It starts at 41,000. Are they right next to each other? Yes. So if I get a leak of something that is in this red section, is there a constant distance from the red section to the section above it? Yes, because they are literally right next to each other. They are contiguous regions of memory. And if we were to look more than just these first two, we see the second one is at 42,000, starts at 42,000, ends at 43,000, starts at 43,000, ends at 44,000, starts at 44,000. And then this one ends at 45,000, and then this has no relation to the next one. This is an important concept to keep in mind. Not specifically that the ELF is contiguous in memory, but that there are many things that are right next to each other, and they will always be right next to each other. This binary happens to be compiled PIE, so we get these 4,000. If I were to recompile this so that it is not PIE, this fact would still be the same, because these are always going to be right next to each other. And so if I were to get a leak of any memory address that is anywhere in any of these 5 sections, I can find things that are in any of the other 4, because there's going to be a fixed constant from one to the other. So PIE is a compilation option. ASLR is a runtime configuration. Let's see if I remember the magic here. I think it's procsys, kernel, randomize VA space. So this right here, which I think is in a Yan video, tells us what is the system currently configured to do. And it tells us 2. You can get 0, 1, or 2. If we man proc, and then we search this thing for randomize VA, it tells us what this means. 0 is ASLR is off. 1 is that some stuff will be randomized, and 2 is we're going to go to town and randomize everything we reasonably can. So ASLR is a configuration of the system, and it will try and everything, for the most part, is going to have ASLR enabled in this course from this point onward. But if a binary is not PIE, can it be randomized? No. The thing that allows the binary to be randomly placed is the way that the assembly instructions are generated. So if the system has ASLR enabled, but the binary is not PIE, the stack will be randomized. The heap will probably be randomized. All these other things will be randomized, but the binary cannot. Does that make some sense about how these two things work together? PIE is a compilation option that allows the ELF to be randomly located in memory. ASLR is the system trying to place everything randomly. And even if the system wants to, if it's not compiled PIE, it simply cannot be randomized. All right, that was a nice little tangent there. Where were we? Object dump a.out, grep win. I get this sweet address. Has everybody converted to Python? Oh, 2 hands. I'll go here first.
Is everything we've done so far had ASLR on it?
The question was, has everything we've done so far had ASLR on it? The answer is no. Okay, so some of the binaries were not compiled PIE, so you didn't have to deal with it. Specifically, like when you're talking about module 1 is like where this would be most relevant. If I make this thing so that it is PIE, actually I don't even need to do that because PIE only influences the ELF. Everything that we've done so far with our buffer overflow has been in the stack. And we've been happy in this nice little purple region. And we haven't had to think about the greater mapping of where things are located in memory. Because we're just thinking about this small little region of the stack, right? We're like, here's the happy little place that I need to live, right? I can write to here and I can go there. And I really don't care what these numbers are because I'm going from A to B and they're right next to each other. So this hasn't been something that's really materially impacted us. And that's by design, right? You got to understand how to corrupt memory, how to think about things and reason about it. But in this module, we're going to start dealing with memory addresses that are located at different spots, and this will be a factor. Good?
Sure. So the reason that we like gathers up the buffer changes at every iteration, but we still see the libraries at constant location. Is that because there is no PIE and hence the code and so the text section itself should not be randomized with ASLR?
Okay.
Am I correct?
Sort of. I'm going to nitpick that one a little bit. So for Twitch, yeah, I see your technical question there on libc canlix. I'm not going down that rabbit hole. Okay. You want to DM me? We can go down there if you want, but not today, sir. The question was, because of ASLR, is that why the stack all the way down here is randomized every time when we run these rock challenges? So I think one of them prints out the stack address, and it's a different number every time, right? And the answer is yes, the stack address is randomized because of ASLR. Right? It doesn't matter if the binary is PIE or not. The stack is a completely different region of memory from the ELF, which is all the way up there at the top, right? They're completely unrelated, so one can be randomized and the other cannot. Now, the part that was kind of not right was you said the word library, and that has a very specific meaning here. So I'm saying the binary, right, the literal ELF that we're executing can be compiled without PIE. Libraries are not the thing that you're actually executing, right? An example of a library would be the loader here, or libc. They have this .so convention, not necessary. Sure, it's an acronym for shared object. That is the equivalent of like on Windows, you have a DLL, right? It's a library that can be loaded in a bunch of different programs dynamically. Well, there's a problem there. If you're going to load a library dynamically in a whole bunch of binaries, can that library really work at a fixed address?
Yeah,
It can't. A library has to be PIE. Because this binary, like imagine a world where every library had a fixed address it had to exist in. How do all the libraries know that they aren't going to conflict with anyone? They couldn't, right? Because there's an unknown, unlimited number of libraries that some arbitrary executable may want to import. And so libraries are always compiled PIE because it's necessary that a library could be loaded into any address because we don't know what else is going to be loaded along with us. Does that make sense? Yes.
That's super quick follow-up.
No, go for it.
If I were to call like syscall read, then how would I know like where to go? Or is it like
That's a good question. So I don't know that I want to get into that one right now. It's a fun one. I don't know when exactly we'll hit it. The short answer is there's a lot of magic that happens. If I disassemble main, You'll notice something weird here. This is still that example binary, I think, unless I decided it's got to be. This doesn't just call puts, does it? It says puts at PLT. Somebody says procedure linkage table. That is, in fact, what it stands for. Because that is like this really hard problem, right? Puts could be anywhere. How do I know where puts is? Well, this PLT thing, if we were to examine 20 instructions here, hopefully I get this right. It doesn't actually go to puts. All right, it's like this little stub where we kind of go here and then we jump somewhere else, and we jump into what's actually the loader, which is this guy down here at the bottom. And then he figures it out and says, oh yeah, here's where it is. And then it overwrites that same section so that next time you don't have to jump into the loader and you know where it is. That is how dynamic linking occurs. And in GDB, with Jeff, there's another thing that's related to this called the GOT, which is where these are resolved. And so we can see for this particular binary, puts has been resolved to somewhere. Right has not been resolved to anywhere. Right? This is going to be inside of libc, so you can run via map with a pointer, and it'll tell you what region it's in. And so that one's resolved, and it goes to read inside of libc. But if we look at this yellow guy here, it does not go to libc. It goes into the binary itself. And that's because we haven't called it yet. We don't need to know where it is. And so this is getting resolved the first time that it's called. It is something that we'll poke at a bit in greater detail and step into that bad boy, but it is a mess to wrap your head around. So we're just gonna say that there's some magic and it figures it out. All right. Yes.
So what are the first fixed addresses in the binary? Like what are those corresponds?
Question. What are the first fixed addresses? I do have to try and get to Rob here. What do you hit me with?
Yeah, these first.
This?
Yeah, these 5, 6, 6 plus 6.
Okay. So these are all parts of the literal ELF, right? I do not know exactly what each one of these are, but I can give you a little bit of reasoning about some of the things that are in these regions of memory. So we have a read-write executable, or not executable, but a read-write region of memory in the ELF. The BSS is going to be there. The BSS is where globals that can be changed and updated at runtime are stored. That's why we need at least a page, which is what we see here. A page is hex 1000. We need at least a page of memory that's read-writeable. That's where globals go, and they can be updated. They'll be chilling in there. We have a read-only. This is literally going to be one of them is going to be the .ro section of the ELF. That is where constants that never get changed are located. The read executable is going to be where our text section is, and there's several more. Those are the ones that I commonly deal with. If you are interested in all of them, let's see if I can run this command correctly. There is a command called readelf. And what it does is it parses the header or the first few bytes of an ELF, which details all sorts of sections, and they do all sorts of fancy things. And you can map these. So like there's where the PLT is located, there's where our text is located in the actual ELF. RO is that read-only data section. There's a whole bunch of sections, some of which you'll care about and some of which you'll probably never have to deal with. And so all of these are getting mapped into these specific regions of memory.
And whatever happens, randomization and randomization, they are always next to each other.
Okay, yeah, the question was what happens when they're randomized. So let's... okay, that's good. We'll make this. We check sec, make sure I did this right. It should be PIE. We are not PIE. Why are we not PIE? No stack protector, that's fine. Did that work? Yes, I have an A dot out. Check sec, A dot out. Why am I still not PIE? Oh no. Not you. That should be PIE. All right, I'm gonna give it one last try here, and then I'm just gonna bail. Okay, we're bailing. The answer is that they will always be in line next to each other because there's the same region of memory that's being mapped. So just like, and it's not specific to this elf, right? That these will always be next to each other. But you'll get a similar phenomenon with, for instance, it would have been easier to just point at libc. Where am I? Libc. 57,000 fad, B1000, B1000, B3000, right? That is just the way that elves are loaded into memory. Because a shared object, even though it ends with .so, is still just an elf. So it's still the same, it's a very similar type of file. And so when these things are loaded into memory, that is the convention. And so it's not just that your executable is located right next to each other, but you'll find if you stare at the output of VM map, there's plenty of happy little regions of memory that are right next to each other. And you can take advantage of that fact. Because I could go from a leak that is, for instance, read-only to something that is read-write, or read-write to something that is executable.
I can stack those into the read.
It's just a matter of like, what do you do with the leak, right? Okay, so let's actually do some ROP in the last 20 minutes. That's okay, because ROP isn't really that hard. So we'll hopefully nail it on the first try. All right, we'll bring up good old IPython. Of course, you're going to write it in a Python file. We'll say from pwn import star, context arch, AMD64. Somewhere down here, we have P equals process, A dot out. And then I'm going to have some payload, which we already established should be A times 256, B times 8, plus, I'm going to use P64, because that's a great number. And let's get that from our object dump dash D, A dot out. Or no, now it's B dot out. And we'll grep win. So I get that constant value. You're going to be like, oh, I already did this. I'll be like, yep, that's ROP. And then we will P send payload. P interactive, right? Good old boilerplate. A dot out does not exist because we changed its name to B dot out. Oh, I segfaulted and didn't get the flag. That's all right. So it'll bring up an interesting thing here. So I claimed at one point that GDB will disable ASLR, right? And if you start the executable with ASLR, now this is PIE, so these are not randomized. That's fine. I'm not looking at them. Looking at these libraries, these are still randomized. The reason for that is what happens when you call GDB debug. What actually happens here? Well, pwn.tools is going to start the binary. Then it's going to attach GDB to the running process. When you attach, the process is already running, which means ASLR is enabled. Now you can deal with that right here in Python. You need two things. One, ASLR equals false. All right, that's pretty cool. The second thing is you can only disable ASLR if it's not SUID, I believe. We'll see if I'm right here. You say SUID equals false. Oh no. Does it set UID? Boom. And now if we VM map, these are going to be fixed repeatable addresses. FC8000. We'll run this again. And FC8000. So if you want to use IPython and debug while disabling ASLR, there is your secret. Why it was not working. Somebody had that late last night. So what's wrong here? What did I do? What did I do? Let's run that guy. Let's disassemble main. Let's break at main plus 52. Let's continue. Let's examine the... well, let's just step into it. Okay, I am in fact inside of Win, so maybe this is just I can't write C code.
Oh, is there that check 1337? I'm not sure if there
So I cheated and gave, or not cheated, but I gave you the source here. There was no check. It wasn't meant to be a troll. Like if I messed it up, I legitimately messed it up.
Are you reading back from the process?
Am I reading back from the process? My Python script ends with PEP interactive, so I should be catching the output. And we're inside open. We finny. Let's look at RAX. Yeah, that's -1, but that's because I think this should be good. We just saw it jump to win, so the problem would be inside of win. Gosh dang it. That's what I get. All right, let's do... We're going to call a challenge function. Challenge is going to do the same thing. I don't think this is it, but we'll go for it. We're going to go back to my make file that's now horrifically broken. No PIE. We make. Now I have an A dot out. Fire on A dot out. Still nothing. Oh, sudo chmod. Oh, I know what I did. I am a silly goose. I chmodded it, but I didn't chown it to root. So chmod u plus s is going to run as hacker. I'm already hacker. It fails to open the flag. Sudo chown root A dot out. Sudo chmod u plus s A dot out. Okay. Can we recover? Okay, the flag exists.
Flag is flag.
Yeah, flag is flag. All right. We are A dot out. If I sudo strace, you probably did something like this similar yourself, right? Yeah. It happens to the best of us. B8, P64, that's a valid hex, that's good. Our context arch, it's fine. Does anyone see it?
What happens if you print the whatever you get before interactive? It's inside your Python script.
You want to print.
Yeah, like I got it from like like your process dot read all and then print that thing.
So receive all will just hang. The closest I can do that'll give us something is while true, we can print P received line.
Like read instead of receive.
Read and receive are synonymous.
Oh,
It is not happy. Does anyone see my mistake here? Okay, you're good. I have to go fresh here. Import star. So what I do is sudo su and then start up by Python. So now I can do this. That's why having a file written is better.
Someone in chat said you changed the source.
I did change the source. I'm reading into the same spot because I added a new frame. Canlex called me there. I need to change back to source to print the flag. I'm reading from the file descriptor into the buff. I'm writing the buff to standard out. That should get me there. Like the only thing I could think of would be like new line buffering, but I should still hit before the seg fault.
Oh, is it like you have to?
What do you got?
No, nothing.
I'd love to know it. I do call you a troll. You're my favorite troll. We send the payload, P interactive, we call it day, and then. Oh, it was there. Okay. So it was some goofy permissions thing. Okay. So we were able to override. I'm just going to hand wave this and be like, all right, man, I don't know what I did. We're not going to go down because I want to get a little bit further. So we were able to overwrite the return address and call that win function. ROP is the natural continuation of this idea. So what if there is no win function? Now we're going to recompile this binary and everything is going to break again. Sudo chown root sudo chmod u plus s a dot out. Cool. Where do I want to go now? I don't have a win function. ROP is this idea of what is the smallest function that we could have. Well, we started off with let's object dump this thing and grep for win. What really defines a function? There's a prologue, there's an epilogue. Is that really necessary? No. The world's shortest function is one assembly instruction and then ret. What does ret do? We just messed with ret here. We abused ret to call win.
It jumps to another address.
It jumps to another address, but how does it know what address to jump to?
It's on the stack.
It's on the stack. Is it literally at RSP? At the time of ret, it is. And we could see that if I scrolled all the way back up when I was debugging it. At the time, right before ret, RSP pointed to the address that I had set there, which was win. Well, in a reasonably large binary, which I'm just realizing now the source of this is bad. In a reasonably large binary, you'll have a bunch of functions, right? You'll have more than just challenge and main. And so what we can do is object dump that thing in Intel syntax. And we can say, well, what is the thing that's right before ret? How many one instruction functions could I make up to? Do I have to jump it to the beginning of a function? No, you probably already saw that from memory corruption. So could I jump to right here? Yeah. What would happen? Well, we'd add 8 to RSP, and then I'd ret. But what happens when I ret? I jump to whatever's at RSP. How about this thing? Can I jump right here? 401.189? Sure. There's nothing stopping me. If I wrote that address over the return address, what would happen? We'd pop RBP, and then we'd ret. What does ret do? It jumps to whatever's at RSP. There's like this pattern here, right? So if we can control what is at RSP, which we already saw we can I control what's the next thing on RSP? Some people are like, yeah, sure, but yeah, I'm baiting you. We can, but how? What do I do to my payload? How do I make that happen? Okay, so this is my BS, and then my payload plus equals this, which is RSP that we will immediately return to. How do I control the thing that's after RSP? What do we got?
Sure. If there's no RBP, just put it right after that.
If there's no
RBP and the function you want to jump to, just put it right after that.
So you're correct that it would go right after this. Because when we write to memory, we write in the positive direction. And the stack grows in the negative direction. So when we ret, which is a pop RIP, we'll go to this location, and then when the stack pointer increments, which makes the stack smaller, RSP will now be pointing to the next thing that we write. And so what we can do is we can write a series of addresses that are these like world's tiniest functions to pull something off. Now, just using object dump to figure this out would be pure pain. There are tools. One that's pretty popular is ROP Gadget. You do need to capitalize ROP. There are several. There's ROP Gadget. There's RP++. These are all installed in the Dojo. And then there is Ropper and Cropper. Cropper is meant for kernel ROP, though. And so I can run this ROP Gadget thing on my binary. And what it is going to do is it's going to search that executable, that ELF file, for, hey, what stuff is there before a jump or ret? So what are those tiny little functions that we can try and invent and come up with, these tiny little pieces? So you remember in shell coding when we had like these constraints, and you're like, I have to write this crazy shell code that no one is ever going to write this? Well, ROP is kind of like that, except now you have zero control over what assembly things you can do. So I see that I could call RAX. Maybe that's useful. I could leave ret. Hopefully, this particular binary, I hid some stuff that is useful, which has pop RBP ret. This is an unusual thing. You won't necessarily see it. And one of the things that you very much so will not see is syscall. normal else binaries, like in user land here, don't call syscalls directly, right? Who does that for them? Like when we called read, how does that happen when the binary is normally working? We talked about the PLT. Where does that go? It goes to libc. It goes to some library. Someone else takes care of actually doing syscall. And so in non-trivial binaries, you will not have this syscall thing. And so we can look at these as tiny little functions that are like, oh, well, if I wrote this address on the stack, I could perform a syscall. If I wrote this address on the stack, I could ret. If I wrote, I don't know, where were the good ones? The old pop guys. We have pop RBP, pop RDI, pop RSI. Now, when you're doing ROP, you'll eventually run into these gadgets where like it does something you like, and then it's also going to do something that's just nasty, right? Like I have to trade off here, like this one right here. I'm popping RDX, then there's a NOP. Do I care about NOP? No, it's literally a no operation. But then it's going to pop RBP. What if I liked RBP where it was? Well, I don't have a choice, right? I have to do these things one after the other. These searching ROP gadget tools do have their own search functionality. Personally, I just pipe it into grep and find what I'm looking for. All right, I've got 4 minutes. Let's see if we can finish this off. So I probably won't go all the way with this thing. What's something that I may want to try and do? May want to try and call, I don't know, open? That's reasonable. What is something I would want to do if I wanted to set up open? I need to set RDI, right? One way I could set RDI is with this super clever gadget, 40111D. Cool. And I'm going to get to the end of this and comment this out. This address is pop RDI. What should my next thing on the stack be and why? This is very important if you want to make progress in the first few levels here. So pop RDI is great because I get to put whatever I want in RDI. What should go after the pop instruction and why? What I want in RDI. So for read, I'd probably want some address that I know is a valid place I can write to. How can I find a valid address on a PIE or a non-PIE binary that I want to write to? Yep. Somebody whispered it all the way there in the back. I could look at VM map because I said the ELF is not randomized. So is this a valid address? Is it read write? Sure. I don't really care what it is. I know I can read there. I know I can write there. And you could envision, as I run out of time, that I could add more gadgets. RSI, pop RSI. What do I got? OX401185. This is my pop RSI. And then I'm going to put the value that I want inside of it. I am making everything a P64 that's going to guarantee that everything I'm writing is 8 bytes because these are not 8-byte numbers, but I need to make sure they take up 8 bytes so that way when I pop things off of the stack, they're 8-byte chunks. The addresses are all 8 bytes in size. If you start writing things that are not properly aligned, you're going to have a bad day. Okay. So with that, I'm out of time. So I'm just going to run this and GDB step through it so that we can see.
It says misspelled payload. payload.
I did misspell payload. Good catch, sir. So we will debug this thing. Hopefully math works. Maybe. Oh, I already have this guy. Or the dojo just does not abide. Oh no. Okay. I don't know if I can save this. It's not splitting because I'm not in. The tmux session is owned by Hacker, but then I sudo sued, so I'm root. So root can't change this tmux session. This is why you should do what I say, not what I do. Put it in a file. Okay. Do.py, go back to tmux, we runner. We're going to disassemble main. We'll break at main, or no, I'm sorry, not main. We'll disassemble challenge because I added that extra frame to it. We'll break at challenge plus 48. We get to there. The first address that I said I was going to do apparently was pop RBP because I can't read. But we get to pop RBP ret. And then the next place I'm going to go is pop RSI ret. And so we see that I'm inventing like this insanity machine of jumping to weird places that are right before ret. And that is determining what this control flow is. And if we were to examine, it looks like I've got a couple more, like 4 giant hex at RSP. This is setting RSI to 0. That's what I'm popping off. This right here is the next place I'm going to jump to because we're going to pop RSI, which is going to pop the 0 in there, and then we'll ret to the next thing on the stack. Now, debugging this is a lot harder than shellcode because I can't just XI from some address and dump it out. Instead, you have to look at what's on the stack and then examine the instruction at that specific address and do that for each entry that you have or step through it. I know I'm keeping you late, but I wanted to at least show Rob Gadgets going through. You caught me, Canlex. I copied pop RBP. It's all over. Anyone have any questions for the stream? Yes.
So the reason that any of this works is because at the ret function there's a pop RIP, right?
The reason that this whole thing works is it's an extension of our existing memory corruption, right? So initially in module 1, we buffer overflowed within 1 frame and we overwrote the 1 return address and we just went to win or went to wherever we wanted to, right? Here, we're saying that there isn't some happy place that's going to do all the work for us. And so we will specifically target locations that have this pattern to it. It doesn't have to be pop, right? This could be move RSI 0 and then ret. It doesn't matter. It is this weird machine, like very much so like when we had the constrained shellcode. We're still constrained on what assembly instructions we can execute just by what's already in the binary. With shellcoding, we're injecting instructions into it and just like, I like these ones, right? But over here, we don't have that opportunity. Instead, it's just like, all right, man, this is what you get. And maybe I need to set RAX to 42, for whatever reason. I don't know what 42 is, but I need to perform a syscall where RAX is 42. If that means I need to call inc RAX and then ret 42 times, that's totally valid, right? As long as what you are doing the magic happens at that same spot where we were before. We're at that first ret This is our first return address that's getting overwritten. And if we were to examine like 8 giant hex at RSP, here's all of the places you'll go and see, right? We'll pop here, we'll go there. We'll pop here, we'll go there, right? Every time that we rent, we're just like, yep, we're going there. Yep, we're going there, right? The thing to be aware of is if you have something that is like pop RDP, what is it going to do? Well, it's going to pull off that same pile, right? But it doesn't need to be a pop instruction that's before the ret. It could be any valid instruction or any valid series of instructions. But the most straightforward thing to show is just, hey, I can set whatever I want to literally what I want. All right. We have 2 weeks to work on this. This is literally the whole thing of Rob. It's just different ways of applying this concept. With that, I appreciate you hanging out. Stream is